So, we shall continue whatever we have trying to cover in the last class, that is deflection of beam, and we are trying to solve the problem with differential equation technique. We have taken a simple beam problem. It was a cantilever with some point load at the end. With that, I have tried to explain you how to find out the final equations, how to find out the constants through boundary conditions, and from there we tried to obtain some standard values of maximum deflection, maximum slope at one of the end. Now, we will try some other standard cases and try to get some important relationship. Technique is same, problem will be little different. Now, I can take again cantilever problem with a little different type of load. So, structure is same, it has a length L, E, I, support identical, it is fixed, that is free, only the loading is different. The idea is to handle a different type of load also, I think, before changing the type of structure. Next step we can change the type of structure. So, our first job is we have to find out the expression for the bending moment, right. Now, at any distance x, so there is one cross section, what will be the expression of bending moment? We can calculate from the right end, because that is a free end, it is easier to calculate. So, beyond that section right side, the loading is, first of all, the length of that will be L minus x, and the loading is say W or omega, that is intensity of the distributed load, the load per unit length. So, length is L minus x and W is per unit length, that is the load. So, total load will be W into L minus x, and that is in a distributed manner. So, moment will be, it is a uniformly distributed load, means we can assume that load is acting at the centroid of that part. Okay. So, it will be acting half distance of L by x. So, we can write omega is the intensity, L minus x is the length, that multiplied by L minus x divided by 2. Okay. So, that is one of the very familiar type of expression. If we start from this side, we will write omega into x, that will be the load into x by 2, or straight away we will write omega x square by 2. In that case, x is not x, it is L minus x. So, it will be omega L minus x square divided by 2. Now, we have to put some sign here. Okay. At this moment, you have to decide which sign convention you will take positive. If you take sagging as positive, it should be negative, because it will give a hogging type of moment. So, if we follow the same thing, it will be minus and minus. I think this part is clear, bending moment expression. Once that expression is ready, we can use that moment curvature relationship. There directly we will put the moment expression. So, there it will be E I d2 y dx square equal to minus m. So, it will be, we can say it is minus m, and we can put here omega L minus x square divided by 2. So, minus minus it will be plus, because sagging we have taken positive, but here moment is hogging. So, we have put minus, and if we sagging as the positive moment, expression will be with minus m. So, this minus minus it will be plus. So, in a similar manner we will integrate as we did in our previous problem. It will be omega L minus x cube divided by 6 minus C1 and EI y equal to omega L minus x 4. So, 4 into 6 24, and minus and minus it will be plus C1 x plus C2. Absolutely same, only the right side part is different. Once you have that expression, our job is to determine C1 and C2, these unknowns, through boundary condition. So, it is in the same manner at x equal to 0, your theta or dy by dx equal to 0. So, this is the first expression or first condition. So, if we put hierarchy, so it will be EI into 0, it will be minus omega L cube divided by 6 plus C1, or we can say C1 equal to omega L cube divided by 6, right. So, your C1 part is available, next part is the C2. So, next requirement or is to find out C2, and that we can find out with the second boundary condition, that is deflection at this point at x equal to 0, it will be equal to 0. So, substitute that boundary condition at x equal to 0, y equal to 0. So, we will get EI into 0, that will be omega L4 24 plus C1 into 0 plus C2, or we can get from here C2 equal to minus omega L4 24, or these values we can put in the expression of slope and deflection. So, it will be 1 by EI minus right. So, C1 and C2 we have substituted the value in the expressions we obtained earlier for slope and deflection, and it will be something like this, that is the expression of theta, that is the expression of your deflection. Now, we will get the maximum deflection, maximum slope. So, you are at x equal to L, theta will be theta max and y will be y max. So, that part if we find out, so theta x, it will be 1 by E I, and here this term will be 0, it will be omega L q by 6, or we can say omega L q divided by 6 E I. Now, if I find out y max, 1 by E I, this part it will be 0 and this part will be omega L to the power 4 divided by 6, omega L to the power 4 divided by 24. So, it is omega L to the power 4. So, 1 by 6 minus 1 by 24. So, if you operate, it will be 24, this side it will be 4 minus 1. So, 3. So, 324 means it will be 8. So, it will be omega L to the power 4 divided by 8. Yeah. So, this is y max, this is theta max. So, this is one of the quantity, that is another important quantity. Right. So, same problem with a distributed load. We have tried to repeat that process with a different moment expression and got the values theta max, y max. Now, I will take a problem where your type of structure will be different. So, beam will not be a cantilever beam, say we will take a simply supported beam. So, two supports at the two end and take some load, say we can take uniformly distributed load, whatever we have taken, at least load will be same like this, but support condition will be different. So, this is a distributed load of intensity omega or W, and the member is some E I is the flexural rigidity. This is the length, this is x, this is y. So, our first job is to determine the expression of bending moment. Now, if we start from this end or the other end, both the side supports are there. So, we have to know the value of those reactions. Earlier case, support was on the left side and one free end was there, we are trying to proceed from the free end, we need not bother how much will be the reaction at the supports. But here we can start from this end or other end, both end are supported. Okay. So, first job is you have to find out the reaction, and that will be utilized for finding out the bending moment expression, and that will go to the differential equation. Now, here there will be one reaction, and here so this part you can say y and this part we can say r, y, it is say r x at say at a, this is b, say left end if we say a, right end if we say b, it is r along x at a, r y at a, this is r b. So, it is a beam problem and loading here are all in vertical directions. So, r x a automatically it will be 0, still we have to put, because there might be some inclination in the loading and that will make the structure unstable, I think. So, we have to keep the provision of some resistance along the horizontal direction. So, anyway this r y a and r b we have to determine here. Okay. So, how we will determine? Okay. You can take moment about any one of the end. So, it is better to take moment about a, at this both the forces will be eliminated. So, first step we can take summation of moment about a equal to 0, right. Now, the reaction R b into L, so that is one force into the length, and that will be balanced by the moment generated by the externally applied load omega. So, that should be equal to, because this is this way moment and load will be given in a different way. So, we can put minus equal to 0 or we can directly put on the other side. Okay. So, we can put here minus, and the omega is the load per unit length into total length L, and its resultant will be acting at the center of the beam, because it is throughout uniform. So, into your L by 2 and total moment will be equal to 0. So, R b you will get from here, it will be omega L by 2, because one L will cancel. So, omega L by 2. Now, the other equation you can apply, it will be say summation of vertical force or all the forces along y is equal to 0. Somewhere you will say summation of b equal to 0, somewhere y equal to 0, sometimes y I, it is a matter of convention. Okay. So, it will be r y a upward, r b upward minus omega into L, it will be downward, whole quantity will be equal to 0. Now, R b already we have obtained. So, r y a plus omega L by 2 minus omega L equal to 0. So, r y a it will be omega L by 2, it will be omega L and it will be omega L by 2, this is minus plus, right side if you take it will be omega L by 2. So, we have tried to use equation of statics, try to write so many equations, ultimately we got both the reactions are omega L by 2. From our basic idea also we know it will be omega L by 2. So, it is you can say verification of that, or from this experience later on we can do one thing. There are some problems where physically we can find out, we need not go for the calculation. So, straight away we will write it is omega L by 2, omega L by 2, okay, because it is quite symmetrical structure fully loaded uniform. So, halfway it will be distributed. So, omega L by 2, omega L by 2. Okay. Now, once these reactions are available, we can write the expression at any point or rather any section. So, we can write the beam in this manner. Here it will be omega L by 2, here it will be omega L by 2, and this part is omega. and here it is x and that side y. So, moment will be at any station, say at any distance at x, this omega L by 2, that reactive force multiplied by x, that will give a moment like this clockwise, and this load it will give a anti-clockwise moment. So, that will be omega x square by 2, because up to here the length is x, omega into x by 2, omega x square by 2, right. So, this is x and per unit length it is omega. So, omega into x will be the load, total load here, that will be acting at the middle of x. So, it will be x by 2. So, omega x into x by 2, omega x square by 2, and this moment will be a sagging moment, right, because this reaction is giving a moment that will generate tensile stress at the bottom. Okay. So, here there is a reaction, this reaction will give a tensile type, and this load it will give tensile, here means hogging type. So, it is we put minus, okay. Right. So, according to sign convention we have written the bending moment expression. So, next step it will be our moment curvature relationship. So, it will be E I d2y dx square will be the minus moment, because sagging is positive. So, it will be minus omega L x by 2 plus omega x square divided by 2. So, once that relation is available, we have to integrate twice. So, it will be E I dy by dx minus omega L x square divided by 4 plus omega x cube divided by 6 plus some constant will come. Okay. Your second level integration, it will come minus omega L x cube 3 into 4 12 plus omega x to the power 4 into 6 24 C1 x plus C2, right. So, next job is to find out the value of C1 and C2 with the help of boundary conditions. In previous problem, we got at x equal to 0 slope deflection, both quantities became 0, but here it is a simply supported problem. So, it will deform like this. So, slope is not 0 here, slope is not 0 here, only deflection is 0 and deflection is 0. So, these two informations we have. So, our boundary condition is at x equal to 0, y equal to 0. This is one of the boundary condition. So, that part we can write here E I y equal to, this will be 0, this will be 0, this will be 0 and C2, and that will lead to C2 equal to 0. Because everywhere it is into x, x cube, x 4, x. So, if x equal to 0, the entire part will be equal to 0, and y equal to 0, C2 will be equal to 0. This is one of the boundary condition. Now, the other boundary condition at x equal to L, y is equal to 0. Now, that boundary condition if we apply, we will have a relatively large expression. So, that expression will be your EI deflection is 0, it will be minus omega L4 divided by 12 plus omega L4 divided by 24 plus C1 L, C2 it became already 0. So, C2 is 0, C1 L omega L to the power 4 by 24 minus omega L to the power by 12, that will be equal to 0. So, C1 we can find out from here. So, C1 will be, this part is 0, this part is 0, 1 L it will cancel, it will be omega L cube divided by 24, because it is 12, it is 24, half of that, and this is minus, it will go to the plus side. So, C1 is omega L to the power 24 and C2 is 0. Now, these two quantities we can put in the expression of our slope and deflection. We will get the equation for the deflection and slope of the deflected line. So, we can write here theta is equal to, because from here already we have the expression, it is 1 by E I, and this part is minus omega L x square by 4 plus omega x 3 divided by 6 plus C1 is omega L cube divided by 24. So, C1 omega L cube divided by 24, and other part we have just put there, and y equal to 1 by EI omega L x cube divided by 12 omega x to the power 4 divided by 24, and this part will be omega L cube 24 x, C2 is 0. So, these are the equations. Definitely you can rearrange in some other form, but I want to find some important parameters. So, what will be the maximum slope, what will be the maximum slope deflection. Now, here the maximum slope will get, where will get it? It will be at the two ends, slope will be maximum at the two ends. So, gradually, so it is a simply supported beam problem. So, here it will be maximum and here it will be 0 slope, and again it will go to the maximum, it will be minus side, and the minus side maximum value will be this. It is a symmetrical one. So, slope this side, it will be identical, only one will be plus, another will be minus, and deflection maximum will get at the center. So, deflection maximum means slope 0. So, that way also we can get it. So, say at x equal to 0, theta will be your theta max. So, theta max will be, here we can put x equal to 0 in that equation. So, it will be 1 by EI, and these two terms will be 0, it will be omega L cube by 24, or sometimes we write omega L cube divided by 24 EI, right. Now, if I write the maximum deflection at x equal to L by 2, your y will be equal to y max. So, it will be at the center of the beam. So, your y max, So, here we have to put 1 by EI minus omega L. So, we have to put L by 2 here. So, it will be L to the power 4 so it is L by 2 to the power 3 it will be 8. So, 8 will come at the denominator, it will be L cube and 1 L is there, it will be L 4 plus omega L 4 divided by 24 is there, and L by 2 4 times. So, it will be 16, right here, and here omega L to the power 4 plus omega L to the power 4, it will be 24 below and 1 2 you will get, because here L by 2 half, it will be 16, it will be 8. Now, all are omega L 4 and it will be EI, only some factors are there, it is 12 into 8, 24 into 16, 24 by 2. So, this calculation if we carry out here, okay, so it will be something like this, it will be omega L to the power 4 divided by EI, and this factor we have to find out. This factor we can calculate here in as a rough calculation. So, denominator is maximum 24 into 16. So, 24 12 means here 2, here 2, it will be 2 into 2 4, right, minus plus 1, and here it is 2 into 8, 24 24, it will be 8. So, it will be 8 plus 1 9, 9 minus 4, it will be 5, and 24 into 16, 24 into 16 if you calculate, so 4 into 6 24 2, 384, I think it will be 384. So, 24 4, so it will be 384, right. So, this is one of the standard form actually, but I want to check whether it is exactly coming on, because this is one of the important term, this is one of the important term. So, 5 by 384 omega L to the power 4 by EI, and that is omega L cube by 24 EI. Okay. So, this is one very very standard case, a simply supported beam with uniformly distributed load, maximum deflection, maximum slope. So, in the next case I will take a point load on a simply supported type of problem, because cantilever we have started with a point load, then distributed load, then we have kept the loading same, support was different. Now, support is again simple support at the both end, but loading is point load. Okay. Now, let us see what are the things we will get. So, the length is L, left end A, it is hinge support. So, R x A, R y A, this is roller R B, x y is like that, P is acting at the mid span. So, it is at the center of the support. Okay. Right. Now, the first job here is to determine the support reactions, because both the end are supported. That we have found in the earlier problem. So, one option is you can take moment at support A, then you can take summation of all the forces, but you need not do it, because from the structure itself or the way load is put there, okay, directly we can calculate. So, what will be the reaction here? It will be straight away P by 2, half load. Okay. So, RB we can write straight away P by 2, and RA it is P by 2, and RXA equal to 0. There is no horizontal force. So, the reactions we obtain from the look of the structure. Next part is we have to get the expression of the bending moment, and that we will substitute in our moment curvature relationship. Here there is one problem. Say this is A, B, the center point is C, and total length is L, and here to here it is say L by 2. Now, your moment expression is not valid for the entire span. So, A to C there will be one expression for bending moment. If you cross C, moment expression will be different. Okay. Cantilever problem point load case was much easier compared to the distributed load, but here situation is just reverse. Okay. Right. So, if we divide into two regions, say x, it is L by 2 0, this is say one part, another part L by 2 L. Here your moment is P divided by 2 into x, that is all, because P into the distance, P into distance, that is giving a sagging type of moment, positive moment. So, it is P by 2 into x. Now, if we cross point C, your moment will be, it is P by 2 into x minus something will be there, okay, that will be P into x minus L by 2. So, additional force will involve additional term in the expression. Okay. Right. So, if you have some other loads, so if you put another load, so we will have one segment, two segment, three segments, or from here there will be a distributed load. So, once a different type of load will come, it will go on inviting one additional term. So, expression will no longer valid there. So, it will be with any additional term means it will be different. Okay. So, for that region we have to apply your moment curvature relationship with this moment, and for the other region you have to put this moment in the moment curvature relationship. So, simultaneously for different segment you have to run it. Okay. Now, let us put the expression and see what is happening. Okay. First of all, your E I d2y dx square equal to minus m. So, it will be minus p x by 2, and this side it will be minus E I d2y dx square equal to minus p x by 2 plus p x minus L by 2. So, this side is more or less same thing, only this part is the additional term. Now, if we integrate, so it will be E I p x square by 4 plus C1, and this side will be EI dy by dx equal to minus P x square by 4 plus P x minus L by 2 square divided by 2 plus say d1. Again if we integrate, so it will be EI into y minus P x cube divided by 12 C1 x plus C2, and here it will be P x cube 12 plus P 6. So it is d1x plus d2. Can you read d2, or it is going beyond limit? Right. Now it is more or less similar type of expression. Here it is up to that, here this plus some quantity, and this region we are getting C1x C2, and here we are getting d1x d2. There might be another segment, it should be say C, D, E, F, G, some sets of constants. So how we will get all these constants? Now here the deformed shape will be something like this. Okay. And if you take the load point, under the load, the deflection if we calculate from the left span and the deflection if we calculate from the right span, they are supposed to be equal. Okay. It cannot be different deflection, okay, because it is a continuous structure. Similarly, the slope if you calculate from the left equation, means equation for the left part, and the slope if you calculate from the equation for the right part, it should be identical, because slope should be identical. There should not be any kink here. Okay. Okay. So there might be a number of span, but in between all those interface point where there is a new load, your expression will change. Your continuity of slope and deflection we can use. Those will give the additional informations like boundary conditions. Right. Now if we utilize those, say at x equal to L by 2, your theta from this side and theta from that side should be equal. Okay. Right. So we can say theta at C from left, it should be equal to theta from at C from right. Okay. So if you calculate from the left side equation, if you calculate theta from the right side equation at C, it should be equal. Okay. So that is the equation. Okay. So if you write that expression, it will be say here it will be minus P L square divided by 4 into 4 into 4, right. So it will be L by 2 means 2 to 4 plus C1, that should be equal to, here it will be again P L square divided by 4 into 4 plus this quantity will be how much? This quantity incidentally it will be equal to 0, okay, because x equal to L by 2, L by 2, L by 2 0 plus d1. Okay. But that should be divided by your EI. because this is slope into ei, both the side it will be divided by ei. So, you can put it again, cancel it. Okay. So, basically this quantity will be equal to this quantity. Now, this PL square by 4 into 4 and PL square by 4 by 4, it is identical, and it is C1, this is 0 D1. So, from here we are getting your D1 equal to C1. Right. So, our equation is different and we are getting different sets of unknowns, but the slope continuity at that point where we are changing our equation, that will give the D1 is equal to C1. Okay. So, first constant in this equation will be identical to that equation on the second equation. So, in a similar manner, if we just equate the y, so at x equal to L by 2, so this quantity and this quantity if we equate, we will get d2 will be equal to c2. So, you can put and see here again, say y at c, it is from left, y c from right. So, here we have the equation, it will be minus p L q divided by 12 into 8 plus C1 L by 2 plus C2, it will be equal to minus p L q 12 into 8. Incidentally, that term will be equal to 0, the additional term what you will get at that point, plus D1 already we have obtained, it is equal to your C1, it is L by 2 plus D2. Now, this C1 and D1 already we have established. So, this term should be equal to this term, okay, and this term is equal to this term, it is 0. So, these two terms should be equal to 0. Okay. So, we are getting D2 equal to C2. The main reason is, I shall show you again this page, previous page, the additional term x minus L by 2, this term will be after L by 2, but at L by 2 exactly the value is 0. Okay. This moment, this load will give some moment on the right side, but it will start from 0 value. Okay. So, when we are putting the boundary condition, that part is becoming 0, whatever additional term we are getting. Okay. So, ultimately it is becoming identical constant within the equation, right. So, there might be say 2 segments like this type of problem, there might be 3 segments or 4 segments. Only first segment will have some expression, second segment will have expression plus some additional term, third one is the expression for the previous zone plus some additional term. So, same thing will be there plus some one additional component plus some constants C1 plus C1x plus C2, D1 x plus D2, like that it will continue, but from the continuity condition all the constants are identical. So, it is this C1, D1, E1, it will be all identical. Similarly, C2, D2, E2, F2, it will be all identical. Now, from there we can think in that manner, we can take the expression of the last span. So, last span it will retain all the quantity of the previous one with some additional component, and the constant whatever we will get, because it will be identical for all the thing. Okay. So, it can be rewritten in this form, say this particular beam problem we can write say M, we can write in this manner. So, for the left span we got, it was m equal to p x by 2. And the right span we got it was minus p x minus L by 2, right, minus. So, it is minus p x L minus 2 and p x by 2. Right. Which one? Extreme reaction, it will not come in the second part. Say here to here m equal to p by 2 into x, and here to here it is, say this force into x, that part is there, minus p into x minus L by 2, because here if it is x, so L by 2 minus, that is the distance p L minus x p, that part it will give a hogging moment and this part will give some sagging moment.
But this RB will also put some moment at that section.
Yeah, because these two force will give some moment, that moment will be balanced by RB. So, if you come from RB, whatever moment you will get, if you come from this side you will get the same moment. So, either you have to take from this side or that side, both the thing you can't take, then it will be cancelling. So, the main part is, this is the expression for the left part, this is the expression for the right part, where right part is involving one additional component. Now, this expression whatever we have written, so we can say this is for left part, and if we take the full component, this plus something, it will be the right part. Now, this equation can be written for the entire structure in that manner. So, whatever we are talking in language, it can be written in some equation form. So, same expression we are telling when it is left support, left span, it is only this one, and right part it is some additional part. Okay. Now, this h L minus x, this is called unit step function, and its value is something like this. Here it is 1 unit, it is L by 2, it is L by 2. So, up to it is 0, then it will be 1, right. That is the reason is very simple. The function is 0 when it is less than L by 2. So, when it is beyond the load, it is 0. When it is beyond the load means it is before the load. When it is after the load, the value is 1. So, here also when it is before the load, only this term. When it is after that load, this plus this quantity. So, that physical logic we are trying to put in a mathematical form with some function called unit step function. So, it will give a general expression for bending moment for the entire span, because both the section your constant will be identical. I think we can stop here at this class. Next class we can continue. More specifically, it is deflection of beam. The method we used, it is basically integration of differential equation. We tried to handle some cantilever type of problem, then switch over to a simply supported case with uniformly distributed load. Point loaded case we have taken very standard type of case, load is acting at the center of the beam. Up to a certain extent we solve it, so remaining part we can continue working. So, last class we got more or less something like this. Okay. So, we took a beam like this side some support, here also some support, and center we put P. Reaction we got P by 2, reaction P by 2. If we say this side is x, that side this is y. Now, the main difficulty what we were discussing in the last class, it has two regions. If we say it is A and if it is B and if it is C. So, A to B there is one segment or a part where your moment has some expression, and the second part B to C, it has a different expression for the bending moment expression. So, these two parts more or less we have tried to express in this manner, say M, that we have written P by 2 into x for the left part. For the right part it was P by 2 into x minus P x L by 2, right. So, that we have written in the last class, because here only one load will generate some moment. So, P by 2 into that distance. So, if x is beyond that limit, here the total length is L and we have divided into two part L by 2 L by 2. Okay. So, the distance we have written earlier, it was say L by 2 L by 2. Now, once we will cross L by 2, the center load P will contribute something in bending moment. So, that was P into L minus your x minus L by 2. Now, after integration we got two sets of constant here and here, left side say C1 C2, right side D1 D2.